All right, so welcome everyone to the monthly meeting of the N3 program. Click in here. It's the second meeting of the year since our showcases, so thank you for joining. The agenda is uh, a welcome right now, what we're doing, and then we're going to do a very quick self-advocacy mini presentation. That was something that the group said that they would want to see. Then we have our guest speaker. That's the bulk of the meeting, Dr. Anthony Campbell from NASA Goddard Space Flight Center Biospheric Science Laboratory and University of Maryland, Baltimore County. And the talk is Remote Sensing of Coastal Wetlands and Global Change. And then we're going to have just a little bit of feedback and then say our goodbyes. The next meeting is going to be Wednesday, December 10th at the same time. Hopefully with someone from the SphereX mission. I don't know if Lynn, this is what I got off the website from SphereX, which sounds amazing. Did you want to say anything about?
They promised me a speaker, but they haven't told me who it is yet.
Okay, so
So
somebody,
I got to go back and nag them.
yeah,
It was like one of two people, but they hadn't quite decided.
right. But it's a pretty cool project. Collecting data on 450 million galaxies and 100 million stars and exploring the
Yeah.
origin of, oops, and it's the origin, not original, of the universe. And then
January
pos
21st, we'll probably have the internship, like applying for other internships meeting.
yeah,
So, and then we'll hopefully have a presentation by one of the interns, maybe Maxwell, because I think he just published a paper,
yeah,
his mentor. So that would be cool if he were to talk about that project. And then probably somebody from, NASA or something about other internship programs.
yes.
So stay tuned about that.
All right. So I'm just going to go quickly through this because I want to give Dr. Campbell as much time as possible. But we do like to have a little bit of information about some executive function things. And it definitely says it's recording, right, on people's things, on when people have yeah.
Yes.
Okay, good. I'm always paranoid that it's not actually recording. All right. So what is self-advocacy? Um, So when you have more independence as you go to college, which a lot of you are going to be doing, you get more responsibility. And a lot of times that's a little bit scary, right? It's really important to be your own advocate. And it gets easier with practice, okay? You change from becoming, you know, counting on your parents or other or teachers to really be advocating for you and to where you're going to be advocating for yourself. And actually, legally, you have to be the advocate for yourself in a lot of cases when you get to be in college. So we're going to just explore that a little bit now. So, self advocacy is the skill of understanding and communicating about your own interests, needs, and rights because you have rights as a person with autism that you are able to exercise in universities in order to get your needs met. Okay, and that is a requirement in the law. So, some characteristics of effective self advocates. You got to believe in yourself. You got to know yourself really well. You have to know how to ask questions and ask for help. All right. It's perfectly fine and acceptable and great to ask for the help you need. It's good to know your rights and remember that rights are not favors. This is what you need to be successful. Don't give up easily, but also keep your cool. Respect the rights and feelings of others and ask for guidance, but make your own decisions. Okay. Educational accommodations are specific changes that remove barriers and provide people with equal access to learning. They don't change what you're learning, only how you're learning. They are not unfair advantages. Okay? That's from the Americans with Disabilities Act, which is what gives you the legal right to advocate for your accommodations. All right, so know your rights. The difference between high school and college looks like, similar. You in both in high school and college, you're entitled to educational accommodations. In high school, parents or guardians are responsible for advocating for accommodations. In college, students are responsible for doing that. Okay? So each individual can choose when, how, and to whom they want to disclose their learning difference. Disclosing to advisors or professors can help with obtaining accommodations, but it's everyone's choice. And you can advocate for the exact accommodations you need without disclosing a specific disability or anything like that. So if you just need extra time on tests, you can just say that that's your accommodation and you don't have to go into all the different issues related to what might be a diagnosis or anything like that. You can just specifically ask for the accommodation that you know works well for you. So, as starts advocating for yourself starts with knowing what helps you learn. So, can you share in the chat maybe some of the strategies or accommodations that you've used to help you learn? I'm going to open the chat here. Give you maybe a minute or so. What are some strategies that people have used currently in your school? Do you have extra time on tests? Do you have someone help with writing or voice to text? Things like that. Okay, yeah, extra time on tests is one of the most common. So there's extra time there. You can also get, have a separate location for tests so you don't have as many distractions. Anyone else use any accommodations? Type instead of handwriting. Yeah. Yep. That's huge. Handwriting can be a real barrier for a lot of people. All right, let me move on. Close this for a sec. So here are some things that you can get, especially, sometimes in college, you don't have quite as many accommodations. Like, for example, some people have scribes in high school, and that often doesn't happen in college. But things like extra time on tests, quiet spaces for tests, recording lectures or getting access to slide decks, seating preferences, because, in like big lecture halls, you might want to be able to sit near the front. And you should also know that along with the accommodations you might get through an office of accessibility or something like that, most universities have lots of resources that are available to everyone. And those might be perfectly fine for you. One-on-one tutoring, workshops, research support through the library, IT help, counseling and mental health. Oops, sorry about that. Career counseling, job hunting, and mentorship programs and things like that. There's definitely like writing centers, things and small group study groups, things like that. Please take advantage of all those things. All right, so we can actually start by advocating for yourself now. So you can share aloud or put in the chat things that you might want to advocate for yourself, whether it's in this meeting, when you're in school, or anything like that. If you can think of things that you'd like to do to advocate for yourself to others. I don't want to spend a ton of time because I want to give Dr. Campbell lots of time to share what he has to say. But you can think about, you don't have to wait for college. Um, Talk to your parents about how they advocate for you now, okay? And, think about how you can actually take on that role instead of your parents. All right? All right. So, guest speaker ground rules. Um, I just want to encourage you, if you have a question, which we will have Q&A time, enter it in the chat or use the raise hand function, and then we'll go in order. But please don't interrupt while Dr. Campbell is giving his presentation. And with that, I'm going to escape and I'm going to encourage uh, Dr. Campbell to take over the sharing responsibilities.
Okay, so you should see my slides now, right?
Yep.
And let me just get to the full screen. Okay. And shrink that. Okay, hello everyone. It's great to be able to share with you all today, and thank you, Lynn and Wendy, for coordinating and inviting me to the monthly seminar here to talk about my research and give you some background on Earth observation, remote sensing for understanding coastal change. So as was mentioned, I'm at the Biospheric Sciences Laboratory at NASA Goddard and at the University of Maryland, Baltimore County. Just some background on myself. I live in Rockville, Maryland, which is nearby with my cat, dog, and wife, all of who are featured here. The cat does a lot of my proofreading, as you can see, and some of the things I enjoy are, games, hikes, and cooking. And I have a PhD in environmental science from the University of Rhode Island, as well as a master's that was focused on remote sensing and GIS from the same institution. And I've been at Goddard Space Flight Center, first as a postdoc and subsequently as an assistant research scientist for the last 5 years in total, and hopefully can continue there. So the things we're going to talk about today are essentially remote sensing for understanding global change in the coastal zone. But I'll first talk about some basics of remote sensing in case you don't have a background or don't aren't super familiar with the concept. And then we're going to focus on talking about the coastal zone to give you some background on that and the systems we're talking about and how they're connected and why it's important to study them. And then we're going to move into coastal wetlands, which are what I study most often, and the importance of these as both a component of the coastal zone and how we use remote sensing to understand their change and why we care about that at all. And this will be partly in a study I did on global salt marsh change with remote sensing, and then we'll also talk about new technologies, NASA airborne campaigns, and how NASA develops sensors and algorithms to understand our environments. So here's a slide of all the different satellites and instruments that are in space that are observing the Earth. These are all focused on the Earth. NASA has many other instruments that are facing out into the solar system that observe the planets and stars, but these remote sensing instruments are Earth observation instruments. So they're essentially we can break them into several categories. One being those that observe the electromagnetic radiation that is passively reflected off the Earth. These would be, optical sensors or passive sensors. And then we have sensors that generate some sort of signal and then receive the response of the signal. These would be things that generate or laser instruments like ISAT-2 or radar instruments like SMAP and let's see some other ones on here, and some of the other instruments, NISAR, which recently launched. So these sensors, the response is very different. One of the longest continuous Earth observation set of sensors is Landsat. And so Landsat's a great one that we use for a lot of our research. It collects a swath of data across the Earth, as you see here. This data, the width of it is called the swath. It collects continuously as it orbits the Earth along a polar orbit. And as time progresses, it fills out the entire Earth out of 30-meter pixels. So each pixel represents 30 by 30 meters on the ground. This sensor is a passive sensor, so it's collecting electromagnetic radiation, and you can see that while it can see the Earth as it overpasses, it also collects the clouds and other atmospheric impacts. So you don't necessarily get a clear image, but it takes approximately 16 days for it to return to the same spot and collect that location again. So that temporal return time is really important when we're looking at understanding change over time. And while Landsat, the original Landsat 1 through 4, collected further back than the time period on here, collected from the 1970s, from their launch in the 1970s, the current iteration of these sensors, which have similar bands of the electromagnetic spectrum that they're collecting, launched in 1984 with Landsat 5, which collected data for a very long time, which we're lucky to have because Landsat 6 was not successfully launched. So that record, that continuous Earth observation record, goes up to Landsat 9, which we saw in the graphic or the movie of collecting across the movie of the swath collection. But you can see the different areas. These bands correspond to sections of the electromagnetic spectrum that are minimally impacted by the atmosphere and tell us certain things about plants or minerals or other aspects of the Earth's surface that are important to be collected, and can understand some of these processes and how they're changing over time. So it's a really important sensor. It's what we'll use in the one study we'll talk about here to understand salt marsh change globally. And one of the other aspects of this that I mentioned was that this is a 30-meter pixel scale. So this field here, you have a nice clear field, and this is very high resolution drone imagery or something like that. And at 30 meters, this gets, slightly less clear. So things like that tree in the center there is just a pixel that looks like a very particular color. But then at 10 meters, which is what the next generation of Landsat will be and what some of the European Space Agency satellites are, you can discern features much more clearly, even though they are somewhat, features like the road and other things can be resolved. So moving on from that brief remote sensing explanation, and really the key part about remote sensing is that we're making measurements about something without ever actually touching it. So there is a level of extrapolation, and we are limited in what we can tell about something through that process. So in the coastal zone, that can be complicated by things like tides and water moving throughout the system and having a relatively dynamic system from the get-go. And the way I like to think about the coastal zone and how we kind of why we monitor it and kind of how we focus in on it is it has a socio-ecological system. So this is linking both the social aspects or the human aspects to the ecological aspects. Every ecosystem across the globe is impacted by humans in some way, and the coastal zone is no different. In many ways, it's even more heavily influenced due to the concentration of human development and industry along the coastal zone. And you can see that here in this graphic here, this cartoon. We have, all these different uses. I'm particularly interested in the intertidal area where coastal wetlands most predominantly reside. This area for humans could be utilized for recreation in beaches and other areas, or it could be utilized for the tidal flats and other areas could be utilized to find bait for fishing in subsistence economies. And then it'd also be an area where nursery species and birds forage. So they're very interconnected in that across the zone, and they also have benefits that cross over into the coastal, that's an inflow from the rivers and into these systems, and the connection of the hydrology and the nutrients across the coastal zone is incredibly important to consider. And the ecological function is dependent on that, but also the social functions are also dependent on kind of the ecology of these systems. And we'll talk about that more in the coastal wetlands focus section. So now looking at another nice graphics, these are all from the Scientific Visualization Studio at Goddard, and these are all available to everybody. So if you ever have a presentation that you want to put a nice graphic into, I would recommend visiting them. But what I wanted to draw everyone's attention to here is just the amount of people. So light, this is an image of the globe at night, observed with the VIR sensor that shows very clearly where lights are changing over these 4 years. But one thing that that we can take away very quickly is that there's a lot of light in the coastal areas. And this corresponds with human activity, but also human population. You can see from that paper in the top left-hand corner, over 2.15 billion people live in the coastal zone. This is very, clear from this image in my mind that the coastal zone is incredibly important for humans. And so yeah, and there's other aspects that of the coastal, important for the coastal zone that we can observe from space. This is a visualization of sea surface height, which is also observable globally and how it's changing from space. Now, if we wanted to understand this better at the local level, we would probably use tidal gauges and monitor it in that way. But it can still be visualized and understood from satellite remote sensing. And here's just another visualization of that 10 centimeters of sea level rise that's happened over the last 3 decades or so. So this may not seem like a whole lot of elevational change, but this can be very important for coastal wetlands, which maybe only have an elevational niche of a meter or so, depending on the tidal range of an area. So with that, I want to start talking about coastal wetlands and transition into talking about some of my own research. And so I kind of mentioned this, maybe not in the most clear way, but when talking about the coastal zone is this interconnectedness. So how do we as humans depend on or benefit from coastal wetlands? So this can be things like the maintenance of biodiversity that these systems provide, whether it's the plants within them or the birds and other species that utilize them for foraging or as nursery habitat, as many fish species do. Those can all be benefits, and those species can transition into deeper waters later in life and be caught. So there's even an economic benefit from the fisheries perspective. They can also benefit water quality, filtering out pollutants and sediments to kind of make increasing water clarity. One of the major things that humans benefit from coastal wetlands, includes salt marshes in the case of most of my research, but also mangroves and seagrasses to a lesser extent, is wave attenuation and storm mitigation. So this is actually, as a big storm, like currently hitting Jamaica, like a big hurricane or something, brings storm surge. This is, increased waves and water being pushed up into the terrestrial environment. These waves are actually mitigated and slowed by the vegetation in the salt marsh environment or the coastal wetland environment. They can also, mitigate the floods, so they can kind of contain some of the water. And while this isn't true, this doesn't happen everywhere across the globe due to the fact that coastal wetlands don't necessarily exist everywhere where we've built. And often we've actually, built our cities on top of these wetlands. So we've lost some of that storm mitigation and coastal resilience that these provide. They're also valued very highly at around $200,000 of benefit per year. And this can be very abstract, but hopefully I've kind of made it clear some of the ways that they can benefit us as humans. One of the other big ones that we'll talk about is carbon, but I'll talk about that in a subsequent slide. And so here is a visualization of, or data collection, another remote sensing instrument, a terrestrial laser scanner that's scanning a wetland in South Africa where we did field work. And you can see the center areas, the black areas that are missing data are where the scans took place. But you can see the individual grassy areas, the kind of valleys of the microtopography that have some succulents. And then here you transition into some areas of reeds and sedges, and then you have a larger patch of the common reed, which is another reed and sedge. So, and then finally it zooms out over a tidal flat area. So across that 100 meters or so, there was quite a bit of variability of species and structure, vegetation structure, and elevational height. And those were all kind of driven by things like salinity, the hydrology, the frequency of inundation in those systems. That all drives that variability, but often we map them as one single habitat. So in our second half, we'll kind of talk more about that and what that means for these benefits that we're mapping. So here we have some examples of coastal ecosystems, wetland ecosystems in particular. The far right, we have a mangrove that is kind of hanging on in a perched water table area and trying to bring the mangrove forest back and recover. We have a cypress swamp in the eastern shore of Maryland, which is a freshwater wetland. And then in the bottom, we have two coastal salt marshes, one with horses from Chincoteague in Maryland and one from South Africa. So just showing some of that variability that's driven by all these different attributes of the coastal region. So one of the services that I didn't mention, but is the focus of some of my research, is carbon. So these systems are, along with salt marshes, along with mangroves and seagrasses, are referred to as blue carbon ecosystems, which is just kind of a nice way to highlight them in a way that they've been kind of marketed in various ways, both in science and in carbon accounting. But the reason they're referred to this way is because their sediments store a vast amount of carbon that's accumulated relatively quickly. And you can see here a soil core, which we collected with a Russian peat auger in South Africa, which shows, the darker areas are where there's, increased sediment. And then this is a relatively sandy core, but those increased, or the darker areas where there's increased organic matter, there's a larger concentration of carbon in those areas, and that's been stored for thousands of years potentially. And we can have several meters of this carbon stored underneath the salt marsh vegetation, and it's not it's a sink, and it's relatively stable as long as these systems are intact. And globally, that carbon amounts to about 1.44 petagrams of carbon. And just like you, that doesn't mean much to me. And it's equivalent to about 10 million acres of forest, which that probably doesn't mean much to you either. And it doesn't mean that much to me, but it's equivalent to essentially the size of Switzerland. And as you know, Switzerland is in the middle of the US, the 51st state. So no, obviously this is a geographic sleight of hand, but that's the approximate size of Switzerland imposed upon the United States. So, and that's essentially how many area of trees, acres of trees that carbon would be equivalent to. But these systems have historically changed, as I mentioned previously, quite a bit. So this is an example of what most historic wetland change would probably look like. Well, not exactly, but it would be a transition or a conversion of the wetland into other land uses for human use. In this case, it's farmland and some aquaculture. In other cases, it would be for urban development or other things. And a lot of this is an example from the Yangtze River Delta in China and a lot of other areas of the globe. And China currently have protections now for these coastal wetlands, less so in the US after some decisions. But there are, there are other loss drivers that are not direct, but still driven by climate change and human activity. So these are things like eutrophication, which are the accumulation of nutrients from either runoff or sewer treatment facilities that can actually cause these systems to be lost due to kind of a growth concentration in the above ground biomass and a loss of below ground biomass. Then also things like climate change. So these systems can be replaced by mangroves, which might benefit from a carbon perspective, but could have unforeseen impacts on biodiversity or even just human use of these systems. And then sea level rise is another major driver. These systems can drown over if there's rapid amounts of sea level rise, but they're also going to shift into the uplands. So there's just a lot of coastal change in that case. And then one of the kind of neat and unique ways that these systems can have been demonstrated to change is herbivory. So both crabs and snails have been known to completely wipe out some areas of them. And so how does this look from above? Because we're interested in monitoring them from Earth observation. You can see here we have erosion, interior changes, interior drowning, so probably from sea level rise, and then some changes which don't necessarily amount to a loss, but shifts in the tidal inlets due to the hydrology of the area. There's also more dramatic changes from things like storm events, which we've mentioned in the past. So this is the example of Hurricane Sandy, which breached the marsh or the barrier island, losing a little bit of marsh, but mostly it was erosion after the opening of the inlet and the changing of the hydrology. It's also processes like overwash, which is the pushing of the sediment and sand onto the marsh surface and the barrier island there. But that's actually going to recover over time often. And in this case, it's actually just a boost of sediment, which gives elevation. So hopefully that's hasn't raised too many new questions, because now I'm going to get into talking about putting some of that knowledge to use and talking about my study on global salt marsh change. This was the majority of my postdoc. We really wanted to understand how salt marshes were changing globally. It was a data gap that had never been explored. There were not unified maps of salt marshes, so we used the best available. There's not a global map of salt marshes, so we used the best available maps and wanted to monitor both loss and gain. So this is discrete changes in salt marsh extent at the 30-meter pixel scale. We ultimately decided to monitor from 2000 to 2019 in 5-year time periods using the Landsat sensor and the normalized difference vegetation index, which is a measurement of vegetation productivity and a ratio of bands, which we'll see in the next slide. We wanted to also calculate how much carbon was being lost or gained in the change in amounts happening. And then the final thing that I was interested in was, are these marshes recovering? A lot of the in situ studies or the studies in the field studies, show that a lot of loss from salt marsh loss from storms and other events can actually recover over years. And so monitoring over 20 years, we should see some recovery. So we wanted to look at that as well. So we looked at, with high resolution, the airborne, how these different change processes kind of look, but a lot of those weren't at the 30-meter pixel scale. So here's a single pixel over time, plotting the NDVI, so the normalized difference vegetation index, which is that ratio of near infrared to red. And this is that same overwash process that we saw in Fire Island in the breach site, but at a different site, and we can see it at 30 meters. So we see very clearly around 1999 or so, this pixel seems to have shifted and changed and becomes unvegetated in this case, so a much lower amount of vegetation. And it never really seems to recover up till 2020 when we stop monitoring. Slow loss processes like interior drowning happen more consistently over time, and you can see, so this would be related to sea level rise, and the previous one would be related to a storm event. So these processes show that we pretty clearly can monitor these things, these loss processes over time. So we applied similar algorithms globally, looking to see if we could find where we could find these changes. On the right-hand side here, you see a high resolution image that then shows our extent we found of loss in Georgia. So that pretty well correlates between the two. We evaluated this globally, so we did get uncertainty metrics. And those kind of end up here, where we found a net loss of 1,452 kilometers squared and a range of between 700 and 2,000 kilometers squared. So these uncertainty metrics were used, and you see pretty nice uncertainties on all of our regions as well. And globally, we also found about 5% of these areas that were lost did recover. But still, even with that recovery, loss was the predominant process. And it's also important to note that the loss in our carbon accounting, we valued it as losing a whole meter, which subsequent studies have shown that it would actually be more likely between 10 and 30 centimeters for some loss types, and then between 40 and 2 meters for other loss types in salt marsh environments. So depending on the kind of magnitude of the loss, it would be a little bit different. But even with that, carbon, or the gained areas, are only gaining carbon from carbon burial. So it takes a very long time to have a meter of soil organic carbon to accumulate, or equivalent. So it's important to preserve these systems and not just allow them to be lost and then think we're going to restore them in a different area, since there is significant value to keeping them in their location. And here's another example of long-term change in a site in the Eastern Shore, and how that looks over on the bottom panels. It's how it looks in high resolution. We also looked at drivers of change. So this is a little bit of a confusing plot, but each dot is a watershed. The x-axis is loss and the y-axis is gain. So those areas, those three points that shoot out in 2004 to 2000, or 2005 to 2009, are actually 3 points in the Gulf of Mexico, 3 watersheds in the Gulf of Mexico, which were impacted by Hurricane Katrina and others in that time period, and had a large amount of loss. So we actually found that hurricanes were a major driver of loss in these systems. This is also a great thing to entertain your cat with. And then here's a plot of all the different areas of salt marsh recovery, which I'm kind of going to just skip over so I can talk about my next topic, which is our work in South Africa. So this was done as part of the Bioscape, which was an airborne campaign in South Africa, focused on biodiversity, led by NASA. It's the first biodiversity-focused airborne campaign. So similar to how NASA tests analogs for astrobiology, Earth systems, tests unique systems on Earth for astrobiology or mineralogy of distant planets. They also test their sensors that are going to be brought into space on airborne platforms. So this is that they tested 4 sensors on 2 different airplanes, measuring both coastal, focused on measuring aquatic systems and terrestrial systems, everything from LiDAR, so those active laser sensors, to optical sensors that measure the entirety of the electromagnetic spectrum. So our research questions for this was, some of the things we really wanted to know was, how well were global maps doing in South Africa? The salt marshes there, from my perspective, were a little different than the European and US salt marshes that most global maps would probably focus on, since those are a predominant amount of the marsh globally, with the US being about 1/3 of all marshes, salt marshes, tidal marshes. So we wanted to test that, evaluate if we needed new baseline data to understand our airborne data, evaluate our field spectra. So we collected, and that's a typo there, from a single estuary, and we wanted to evaluate if that was useful for monitoring the entire region, which was collected with the airborne sensor. And we'll look at that and validate those maps with field plot data. And we also wanted to understand, how, and start working on developing algorithms to understand species richness across these systems. So in this case, we'll show some of the results from that and evaluate this early question, which is, could we apply some of these sensors to already spaceborne platforms? So this is just some of the kind of plots we looked at, and the species and vegetation types that are across the area of South Africa we saw, and some of the variability. So we saw some of this in the terrestrial laser scan data, but all of these so far would that's kind of just Bermuda grass. But most of these are salt marsh plants and in salt marsh environments. Uh, and we're collecting the plots here. And then, but there's quite a bit of variability across it. And then here, the PhD, Patty Takali, a PhD student from South Africa, is collecting imaging spectroscopy data at the plot level. We collected many of these scans of individual vegetation types to relate to our airborne data that was flown within 2 weeks of us collecting this data. Another example of that. Also, so those were all of our salt marsh plants. We also looked at submerged aquatic vegetation. I think this is eelgrass. And then we also looked at reeds and sedges, and this is the common reed Phragmites. The plot, it doesn't photograph quite as well because you're in the thick of it. And it's about, in this case, this was about, 3-4 meters tall. To kind of evaluate this, we first wanted a baseline. We decided when looking at the global maps that we needed a baseline that was that utilized high resolution data. So we used PlanetScope data, which is a commercial data provider that's available through the commercial satellite data acquisitions program at NASA. And we downloaded around 3,000 images from this across December to February of 2023, which corresponded approximately with when we were doing field data. We used a machine learning and deep learning approach to kind of map these systems, focused on those 3 vegetation types: submerged aquatic vegetation, salt marsh, and then reeds and sedges. So these are very different structurally, and they're different from what species they would exist in those and where they fall on the tidal range or the tidal across the intertidal zonations. So this ultimately results in something like this, where we have predictions of each of these classes for each of these images, and we summed these up. To get a probability of occurrence for each of these species, and then eventually calculated discrete classes, which we evaluated across time and space for things like estuarine type. So we don't really have time to get into all of this, but depending on the geomorphic setting, the freshwater inflow, the tidal inflow, and many other things, estuaries have very different patterns of salt marsh vegetation, is what we found. So this meant that things like the estuarine bay and the lagoon, which are permanently open estuaries, they're always connected to the sea. And they're dominated by that connection. Those had much more salt marsh vegetation, and we mapped them in that way. So that wasn't surprising, but what was surprising was that reeds and sedges were really the dominant coastal wetland across our study region. So this changes everything, because when we did our field plots, it was also clear that those were the areas that had less species richness, less variety in the vegetation types across them. So it means that our salt marsh, where we had a larger range of vegetation, was probably had much less extent and could potentially be more vulnerable to change. We also looked at how these were protected by how these systems were protected. So this was an evaluation done by South African colleagues who looked at each of the estuaries, and if it was well protected, so had significant protective status. And for the most part, very little of our estuaries were, but many of them were moderately and poorly protected. So there is an avenue for further protection, putting these into national parks with greater restrictions on use or something along those lines. Although they do serve an important purpose to these ecosystems, as I said, getting bait fish or something and fishing out of them and off them was something that we definitely saw while we were doing field work. So there is an importance to allowing that access still, but there is some room to protect them. The not protected estuaries, there's room to protect them. So that would be beneficial. So talked a bit about field work. kind of the summary of these of our field work is we collected 64 vegetation plots and identifying species, percent cover, vegetation height. We also collected those species and plot level spectra, as you kind of saw in those images. See here a graph of one of our estuarine sites and our kind of trajectory across several days where we collected. It was kind of clustered in that one area because of access. It's very hard to get into marsh areas if you haven't trekked through one. It's an experience. And we collected these, very close to the overflights of the airborne sensors, and we also collected soil cores. So that spectral library, we accumulate all those spectral signatures for around 10 per species, and for around 30 plus species. We then aggregated these into spectral classes. So these are wetland classes corresponded with inundation. So intertidal were those that were most frequently inundated. Upper intertidal are those that are inundated once a day, and then or less frequently than the intertidal, and then subtidal are marshes that are really outside of frequent inundation. So those three were our habitats of most interest, with reeds and sedges, which we saw in the previous classification approach. So we kind of wanted to refine and improve on our coarser classes by bringing in more differentiation of especially the salt marsh species, which had so much importance. So to apply these spectral library that we developed using that field data, we used a spectral mixture analysis, which evaluates every pixel in the airborne data and compares it to our spectral library, determining how similar it is to those spectral library signatures that we have. So each pixel gets a value for each of our spectral end members, and we can evaluate that in the uncertainty of that with repeat simulations using slightly tweaked parameters. So that we collected, we applied this metric, and it results in something like this, which is this is just three of our classes. So we obviously have more classes. These are the three coastal the three salt marsh classes, and you can see their distribution across Longevon Lagoon, which is where we took our field data, and it matches what we would expect, although it's a little bit more extensive in the intertidal area because we did not have a submerged aquatic vegetation class. So it expands kind of into some of that submerged aquatic areas where we expect there to be more submerged aquatic vegetation. But we collected, or the airborne data also collected a image at higher tide, and this drastically changed where we mapped. So this is something we obviously know from from many years since Earth observations had been collecting in the coastal zone and been an area of interest. It's been very clear that the tides are a major concern, and this was collected with 2 days apart from one another, but at very different. But the image looks completely different, and we don't map any of those intertidal areas, or we map much less of the intertidal area. So this is a major concern, and it was something we wanted to compare and look at, and we'll kind of do some comparisons that. And then we have another result for the estuarine lake. We also verified this data looking at our plot data, finding around an 80% accuracy, which isn't great, but for this kind of community level classification, it's not too poor, and the uncertainty metrics and other things allow us to have greater confidence in some areas. We also wanted to predict species richness, in this case, Shannon Diversity Index, which is a index that is a little less impacted by extremes of species richness, and we wanted to see if we could predict this with our spectral data. We did a decent job of doing it with just our classification, but when we added our planet scope classification from the beginning of this section, our ability to predict this species or Shannon Diversity Index went up quite a bit. And this is what the results of those look like. And essentially, when comparing across our three estuaries of most interest, that we conducted field work in, we saw that the one with the highest proportion of high species rich areas was this one, Neisner Estuary, which has quite a bit of intertidal areas. Our least species, least area, our estuary with the least species rich areas was Swartblay, which is an estuarine lake. So it's not always connected to the ocean. It sometimes gets closed off. And then right in between these two was our Langevin Lagoon, which has our most extensive salt marsh, but did not have the most species rich areas. And the species richness varied by tidal stage, which is concerning because we would like these to be consistent metrics across tidal stages ideally, but that's a lot to ask. And very briefly, I'm going to talk about some of the results for the Elvis data, which is a waveform LiDAR. So this shoots a beam of light down at the Earth that then returns and gives you a measurement of the ground and the vegetation structure and vegetation height. We have measured vegetation heights in all of our plots and resulted in a pretty good fit between the Elvis data and our vegetation height data. We won't dwell a whole lot on that but we can bring that together with our vegetation classifications and those two dates of two different tidal stages to do a map like this. So the yellow is submerged aquatic vegetation, or seagrasses in this case. The two blues are the two different tidal stages of water. The green area is salt marsh, adjusted for the bias that we saw in our comparison of field data to Elvis data. And then the purple is reeds and sedges, which are much taller and were actually adjusted up in height. So just one of the examples of things you can do. So our major takeaways here is, the future of monitoring the coastal zone with these new sensors, whether imaging spectroscopy, and as those get launched, or LiDAR is, really can be really impactful. When sensors developed on these airborne platforms do become satellite based and we have more consistent monitoring of these systems, there's really a promising new approach to understanding the species richness and kind of impacts of tides and other things on these systems, which is hugely exciting for me. So any questions? Thanks, everyone.
Wow, that was great and such great visualization.
It's a lot.
Plus, you've traveled all over the place to take all these measurements, which is a super cool thing too.
Yeah, it's definitely some exciting travel. You get coastal wetlands, you get to go to beautiful places for sure.
Any questions, anybody? Very quiet bunch tonight.
I have a question. When people would use the term like draining the swamps, is that like basically getting rid of the wetlands? Like, because back in,
They would
like
be, I
the
mean, wetlands
fens were
were,
drained in England, and that kind of
yeah,
thing, right?
no, exactly. Yeah. It's kind of this idea of the wastelands, right? Like historically, wetlands were considered wastelands. So, reclamation is the historic term for wetlands. And I remember my first paper I was writing about wetlands. I used that term because it is common and still gets used a lot, but it's very assuming there's no value in something you're reclaiming, or so it is kind of important to think about them as we're converting these things. We're not reclaiming them from the sea. They weren't something that was ours that we lost. It's has an important use. So I mean, there's many large land uses that we have on wetlands. Like the one I started my research in Jamaica Bay in New York City, nestled in New York City. And JFK is a historic wetland, right? So it was a massive, they emptied out areas of the bay and dumped it on. But if you look at that bay, basically the entire, all along the coast is infilled and very few wetlands, but it was all historically wet. So really anywhere you look where we have a city, there's a lot of change that we conducted often before we have a satellite record. So the reason that Yangtze River Delta is so dramatic is it's in the satellite record. So some of the change that China's done to coastal wetlands is in the satellite record in a way that the US and Europe, we changed in similar ways, but it's out of the satellite record. So,
It's just so interesting because the history of, human development, they're always talking about draining swamps and claiming land as like a progress, right? Instead of as
yeah.
destruction, you know.
Yeah, and I mean it has a purpose, right? I mean, there's reasons that we did those land use change. It's you can't think about it as an absolute, but yeah, ideally we'd have more wetlands, but that's maybe my bias. But